In this lesson, we'll explore how data can differ even when the center looks the same. You'll learn how range, interquartile range, skewness, box plots, and standard deviation help you understand how data is truly spread out. When two data sets share the same mean or median, they can appear similar at first glance. However, that similarity is often misleading. The center tells us where the data is located, but it does not tell us how the data behaves. Spread describes how much the values vary around the center, and it reveals patterns that a single number cannot capture. One dataset may be tightly clustered, showing consistency, while another may be widely dispersed, showing instability, even though their averages match. On the SAT, many incorrect answers come from focusing only on the center and ignoring variability. To interpret data correctly, we must look beyond where the data is centered and understand how widely it is spread. Range is the simplest measure of spread. It is calculated by subtracting the minimum value from the maximum value, and it tells us the total width of the dataset. In the first example, the data values are tightly grouped between the minimum and the maximum. Because the values stay close together, the range is small, which suggests low variability. Now look at the second example. Almost all of the values are exactly the same as before, but one extreme outlier appears far to the right. Even though the majority of the data did not change at all, the range increases dramatically. This happens because range only considers the two extreme values and completely ignores what happens in between. As a result, range can exaggerate how spread out the data really is. Many SAT mistakes happen when students compare ranges without noticing outliers. Range is useful for quick checks, but it should never be trusted when extreme values are present. This limitation is exactly why we need more robust measures of spread. Interquartile range, or IQR, is a more reliable measure of spread than range. Instead of focusing on the minimum and maximum values, IQR looks at the middle 50% of the data. It is calculated by subtracting the first quartile, Q1, from the third quartile, Q3. This box represents where the majority of the data actually lives. In the first example, shown without any outliers, the whiskers extend from the minimum to the maximum value of the data. Here, the maximum simply means the largest observed value. Now compare this with the second example. A very large value, 40, appears far to the right. This value is classified as an outlier because it falls far outside the typical range of the data. Because it is an outlier, it is not included in the whiskers. Instead, the whisker stops at the largest value that is not an outlier. This means that in this case, the label, max, does not represent the true maximum value. It represents the maximum non-outlier value. The outlier itself is shown separately as a single point beyond the whisker. Even though the overall range becomes much larger, the box itself stays exactly the same. This tells us that the core of the data did not change at all. By ignoring extreme values, IQR prevents a single outlier from distorting our interpretation. On the SAT, this makes IQR especially useful when comparing variability between datasets that contain outliers. In the next section, we will look more closely at how box plots define and display these components. A box plot is a powerful visual tool for understanding both the center and the spread of a dataset. Unlike range, which only looks at extreme values, a box plot focuses on how the data is distributed overall. The box itself represents the interquartile range, or IQR, which contains the middle 50% of the data. This tells us where most of the values are concentrated and how consistent the data is. The line inside the box marks the median, showing the central position of the data. By comparing the median's position within the box, we can begin to see whether the data is symmetric or skewed. Extending from the box are the whiskers, which show how far the data spreads beyond the IQR. Long whiskers on one side indicate that the data stretches further in that direction. Values that fall far outside the whiskers are shown separately as outliers. This separation is important because it prevents extreme values from distorting our view of the typical data. By looking at a box plot, we can quickly compare spread, detect skewness, and identify unusual values, all without calculations. On the SAT, this makes box plots one of the most efficient tools for comparing distributions accurately. Skewness describes the overall shape of a data distribution. Instead of focusing on how wide the data is, skewness tells us which direction the data leans. When data is skewed, values are not evenly distributed around the center. One side of the distribution stretches farther than the other. In a right-skewed distribution, the tail extends to the right. Now look at the graph. The solid green vertical line represents the median, and the dashed red line represents the mean. In this right-skewed example, you can see that the mean, shown by the red line, is pulled to the right toward the tail. This makes the mean larger than the median. The median, shown by the green line, stays closer to where most of the data is clustered. In a left-skewed distribution, the opposite happens. A few unusually small values stretch the distribution to the left. The mean, again shown by the red line, is pulled in the direction of the tail, making it smaller than the median, shown by the green line. It is important to remember that skewness is named after the direction of the tail, not the direction of the peak. This is a very common source of confusion on the SAT. When data is skewed, the mean becomes unreliable because it reacts strongly to extreme values. The median, on the other hand, remains stable and better represents the typical value. That is why, on the SAT, skewed data often signals that the median is the most appropriate measure of center. Standard deviation describes how spread out data values are from the mean. It does not describe where the center is, but how far values typically fall from that center. Look at the two datasets shown here. Both datasets have the same mean, located at the same position. At first glance, they may appear similar, but this impression is misleading. In the top dataset, most values are close to the mean. The distances from the center are small and consistent. Because the data is tightly clustered, the standard deviation is small. In the bottom dataset, the mean has not changed at all. However, the values are spread much farther from the center. Some values are far above the mean, and others are far below it. These larger distances increase the standard deviation. Standard deviation measures this typical distance from the mean. When values are more widely spread out, the standard deviation is larger. On the SAT, you do not need formulas to see this. Compare the spread visually. The dataset with values farther from the mean will always have the larger standard deviation. Before we move on, let's take a moment to clearly summarize what we've learned about spread and variability. First, we saw that having the same mean or median does not mean that two datasets behave the same way. The center alone never tells the full story. We learned that range is easy to compute, but it can be strongly affected by a single outlier. One extreme value can make the data appear far more spread out than it actually is. That is why interquartile range is often a better choice. IQR focuses on the middle of the data and ignores extreme values, giving a more reliable picture of typical spread. Box plots help us see these ideas visually. They show the median, the spread of the middle data, and the presence of outliers all at once. We also learned that skewness changes how the mean and median relate to each other. In skewed data, the median often represents the center more accurately than the mean. Finally, standard deviation helped us think about spread as distance from the mean. It tells us how far data values typically fall from the center. With these tools in mind, we are now ready to apply them in practice. Look at the two histograms on the right. Which class shows greater variability, and why? Use evidence from the graph, think about spread, range, and how far the scores extend from the center. The correct answer is Class B. To solve this problem, it is important to remember what variability means. Variability is not about where the center is. It is about how spread out the data values are. When you look at the two histograms on the right, notice that both classes have a similar center. This might make the distributions look similar at first. However, the question is asking you to compare spread, not the average. Now focus on the width of each histogram. In Class A, most of the scores are clustered close to the center. The bars do not extend very far to the left or to the right. This means the scores are relatively consistent. In contrast, Class B's histogram covers a wider range of values. The scores extend farther away from the center on both sides. Some values are much lower, and some are much higher. This wider spread tells us that the data values in Class B vary more. That is exactly what greater variability means. On the SAT, always remember this strategy. When comparing variability, compare the overall spread of the distribution, not the height of the bars and not the center alone. Because Class B has the wider distribution, Class B shows greater variability. The box plots show the test score distributions of two classes. Both classes have a similar center. Which class shows greater variability, and why? Now let's go through the answers step by step. Both Class A and Class B have the same median. That tells us their centers are aligned at the same value. So this problem is not about comparing averages or typical scores. It is about variability, which means how spread out the data is. When you are given box plots, the most important feature to examine first is the interquartile range, or IQR. The IQR represents the middle 50% of the data and is shown by the width of the box. In this case, Class B has a clearly wider box than Class A. That means the middle 50% of scores in Class B is spread out over a larger range of values. This alone indicates greater variability. Next, look at the whiskers. Class B also has longer whiskers than Class A. This shows that the overall range of the data is larger as well, with scores extending farther away from the center. Even though both classes share the same median, the data in Class B is more dispersed around that center. So the correct answer is Class B, because it shows greater variability. On the SAT, remember this key strategy. When comparing box plots, focus on the IQR and overall spread first, not the median and not formulas. Now let's move on to an advanced SAT practice problem. At this level, you are expected to choose the most appropriate measure of center, not just identify one by formula. Notice that the distribution is skewed and includes a clear outlier on the right. Take a moment to analyze how this affects the mean and the median, and decide which measure best represents the typical score, and why. Let's carefully go through the correct answer. In this situation, the most appropriate measure of center is the median. First, look at the shape of the distribution. The histogram shows a right-skewed distribution, which means most of the data values are concentrated on the lower end, while the tail extends toward higher scores. Next, notice that there is a high outlier on the right side. This value is far away from the rest of the data. Outliers like this have a strong influence on the mean. Because the mean is calculated using all data values, a single extreme score can pull the mean in its direction. In this case, the high outlier pulls the mean to the right, making the mean larger than what most students actually scored. As a result, the mean no longer represents the typical score very well. The median, on the other hand, behaves differently. The median depends only on the order of the data, not on the exact size of extreme values. This makes the median resistant to outliers. Even with skewness or extreme values present, the median stays close to where most of the data is located. That is why the median gives a more accurate description of the center of this distribution. On the SAT, this idea is extremely important. Whenever you see a distribution that is skewed or includes one or more outliers, you should immediately question whether the mean is appropriate. In most of these cases, the median is the better choice. So the correct answer is the median, because it best represents the typical score in a skewed distribution with an outlier. Let's wrap up this lesson by focusing on what variability really means. Variability is about how spread out the data values are, not where the center happens to be. Two datasets can have the same center and still behave very differently. That's why spread matters. The range gives you a quick sense of spread, but it can change a lot because of a single extreme value. The interquartile range, or IQR, is more reliable. It focuses on the middle 50% of the data and is much less affected by outliers. Box plots are especially powerful on the SAT. They allow you to compare spread and center visually, often without doing any calculations at all. Standard deviation goes one step further. It measures how far data values typically fall from the mean and helps you compare overall variability more precisely. On the SAT, strong problem solvers don't rush to compute. They first look at the distribution, compare the spread, and then decide which measures make sense. Mastering variability gives you a deeper understanding of data and a clear advantage on SAT data analysis questions.